So we'll start a new series about chemistry here, and this will be the first video about chemical equilibriums. And when we're talking about chemical equilibrium, we're not talking about, oh, the concentrations are the same on either side of the reaction, such as, we have the same amount of hydrogen and oxygen as we do water. That is not how equilibrium works. Equilibrium, in a chemistry point of view, means that the forward reaction, the reaction of the process that we know, is going at the same rate as the reaction in the opposite direction. And the concentrations, although they're not the same on the reactants and the products, they stay the same. They do not change. And so we have three topics here that we will discuss, considering the fact that not a lot of people do well with this unit. And we'll start off with equilibrium constant K and the product Q, then acids and bases, and then solubility. And so let's get into this, starting off with equilibrium constant K and the product Q. And so we're starting off with the equilibrium constant K and the product Q, and we have three subtopics for one of these three topics. Lots of things to go over for this unit. We have calculating K and Q, favorability of a reaction, meaning favoring the products or favoring the reactants, meaning favoring one, meaning although the reaction rates are going at the same, speed, I guess you would say, one of the reactions is more favorable. We'll just have more products or more reactants, either one. And then we'll get into ICE tables, and that will end off this video for this unit, and then we will cover the rest of the parts in other videos. And so let's get into it. So how do we calculate K and Q? Well, K and Q are calculated in the same manner. But K is an equilibrium constant, meaning that this value of K is always constant when the reaction is at equilibrium. Always constant, unless you add something to the reaction, take away something. Unless you manipulate the reaction somehow, or the concentrations, or you somehow manipulate something, not manipulate the speed. The speed will still keep K constant. If you add a catalyst, you will still get the same equilibrium constant that you had before. But if you add more products or add more reactants, or take away products or take away reactants, then K is going to change to, fit the reaction. Q is always constantly fluctuating depending on how the reaction is going. Over time, Q becomes closer and closer to K because Q is the product of the reaction before it hits equilibrium. So Q is always getting closer and closer to K. So how do we calculate it? Well, the formula is quite simple. Q, and then we'll say C, meaning in concentration. So the equilibrium product in terms of concentration of the reactants and products is equal to, for say we have the reaction A, so we have coefficient A, compound or molecule A, plus B. This is the equilibrium sign, meaning forward and reverse reaction, like that. So this is what we have for our reaction, and so now we will apply this to this. So what do? Well, we start off with the products because that is our final, right? We always do final minus the initial, but in this case, we don't do final minus initial. We do final divided by the initial. The next step after subtraction is division. Same thing with addition and then multiplication, because this is sort of like the next step. So if you if you do Hess's law, right? So if you do Hess's law with two reactions and then you have the equilibrium constants or products, right? And you add the two reactions together, the two products or constants actually multiply, right? So you go straight to the next step. So this is going to be, right? So we have the concentration of C, and what's the next step after multiplication? Exponentiation to the power of C, power of D over the reactants. Okay, that's how you calculate it, just like that. And so if we know the reaction, if we know the reaction, yes, and the concentration, we can calculate Q. And then we know that it's at equilibrium that Q is equal to K. So at equilibrium, Q is equal to K. And so now we have favorability of a reaction, which is the second part of equilibrium constant K and product Q. So we have 6 different cases here. So the first of all is K is equal to 1. So when K is equal to 1, that means that we have the same amount of products as we do reactants. That means that our reaction is favorable towards any side. The reaction is very, very even. It's an equal reaction. The forward reaction yields the same amount of product as the reverse reaction, and you also end up with something that, well, it's not dissociation. Dissociation is like Q is infinity because you essentially don't have any reactant left, right? In this case, when K is equal to 1, 50% of your reaction at equilibrium, 50% of what is in, the container that the reaction took place in is going to be your reactants, and the other 50% is your products. When K is greater than 1, it means that your reaction favors the products. Because the products are in the numerator, that means that if K is greater than 1, the numerator must be greater than the denominator. That's how fractions work. And so therefore, this means that this reaction has more products formed than reactants. That doesn't mean that you're going to run out of reactants. It just means that the products are going to be more prevalent in the solution, or whatever the container that in which the reaction took place is going to be mostly products. That's basically it. When K is less than 1, mostly reactants. It's the same thing, just the opposite. So now let's get into the relationship between Q and K, what that has to do with favorability. So when Q is greater than K, it means that you have more products currently than you do at equilibrium. So what that means is that you are forming more reactants. Now that doesn't necessarily mean that it's favoring the reactants or the products. It just means that it's forming more reactants in order to create an equilibrium, reaction, in order to set up equilibrium. That's it. And when I say equilibrium, we're talking about dynamic equilibrium, where it's still constantly going. It doesn't just stop. It's always going. The forward and the reverse reactions are always going, always, all the time, until you stop it somehow. I don't know. Anyways, Q is greater than K, shifting towards the reactants. Q is equal to K. That means we're at equilibrium. Q is less than K. That means that we are forming more products. It means that originally you had more reactants, and now you're forming more products. So now we'll get into the last part of the equilibrium constant K and product Q. So say we have this reaction currently not at equilibrium, okay? So we'll set up this chart known as an ICE, or ICE table. And so this is your I, meaning your initial concentration, your C, meaning your change in concentration, and your E, meaning your equilibrium concentration. Okay? This space is not used. So this is going to be AgCl, silver chloride. This is ammonium nitrate. This is silver nitrate. And this is ammonium chloride. Okay? So say we have 0 of this at the start and none of this at the start. And we have 0.1 molar silver chloride and 0.05 molar ammonium nitrate, okay? So what is the change? Well, this reaction does not occur all the time. This is not a 100% favorable reaction to the right. And so, what we do here is we subtract x, because we don't know how much we lose, and we subtract x here, because we're losing reactants to form more products. Always, because this is the forward reaction, we always go in the direction of the forward reaction. If it were the opposite way, and we still had these, then it would go the opposite way. Okay? Minus x plus x. And so at equilibrium, this has a concentration of 0.1 minus x molar, and this has a concentration of 0.05 minus x molar, and this has a concentration of x molar, and this has x molar. And so I've erased the reactions so I have enough space to write. And so we'll take our ice table. So we have x here, right, for the equilibrium concentration. And so in our Q product, in our reaction, the equation for the K and Q, we'll say K is equal to, because we're at equilibrium, so K is equal to the products over the reactants. And if you remember the formula, it's going to be the concentration to the power of the coefficient. What are the coefficient in front of all these? 1, so it doesn't really matter. So this is x times x, so that's just x squared, over, and this is 0.05 minus x and 0.1 minus x. So this is 0.1 minus x and 0.05 minus x. And if we were given the concentration, we could actually find the change. And we could actually calculate what the equilibrium concentration for these products are. And this is going to be very useful when we deal with acids and bases.